Welcome back. Previously, we learned how to go from line structure to a Fischer projection, that is to go from a three-dimensional structure to a two-dimensional structure. This time around, we're doing the opposite. That is, we're going from a Fischer to a line, that is going from a 2D to a 3D structure. The rules are pretty much the same, except we have to make a few more adjustments. Assign number to all the carbons. Now, what I mean by number of carbons here is there will be pivot points on the spinal cord for each molecule, right? That's basically where you assign numbers so you know how many carbons you have. So you're going from top to bottom in a straight line. And then you determine RNS, and I'm going to teach you what subtle changes you have to make to determine RNS. And then we draw a rough line structure, and then we will adjust it to match the RNS on the Fischer projection. And like I did previously, I'm going to work one problem in this video and one more in the next video, and then we are going to leave you with a few practice problems. And if you have any questions, you can bring it up in class or during when you turn in your thoughts. Without further ado, let's get started. That's our structure. Don't worry about the names. I'm not going to test your names on these. This is a sugar. It's a different form of a sugar. So if you go from top to bottom, it's 1, 2, 3, 4, and 5. So I have 5 carbons total in my molecule. So you need to know that, because when you draw your line structure, you need to match to have 5 carbons. Now, how do we determine RNS? Now, remember, first, to determine RNS, the carbon has to be chiral. So only 2, 3, and 4 are chiral carbons. Okay. Now, a tip for you: the molecule that's always in the vertical position, which is usually the 1 and whatever the last is, they will never be chiral. Okay. So don't even waste your time doing it. It's always the ones in the flat lines. Sometimes even the flat lines could be 2 hydrogens on either side, so you have to watch out for it. But 98% of the time, it's not the case. So it doesn't matter whether the hydrogen in the flat line is on the left side or the right side. Okay, left or right, we're going to assume the hydrogen is always in the front position, just to make our life easy, so we can determine RNS. Okay, so this is front. Okay. Right, so let's continue our journey. So this is 1, this is 2, this is 3, and obviously hydrogen is 4. So this is clockwise. So clockwise front is S. Let's continue our journey further down. Again, this is 1, this is 2, because this has got everything the same, but it's got a double bond O, so it's 2, 3, and hydrogen is in the front, and that's 4. So 1, 2, 3, again, this is counterclockwise and front, right? Counterclockwise front would be R. And let's go further down, 1, and this is obviously 2, 3, and 4, and hydrogen will be in the front. Again, that's again a counterclockwise and front, so that's R. So we have S, R, and R. Those are for 2, 3, 4 respectively. Okay, for the Fischer projection. Now let's go and draw 5 dots, so we have 5 carbons. Doesn't matter whether you start from the top and go down, or it's all, see, don't get caught up in all the cosmetics. Okay, 5 carbons means your molecule has 5 carbons. It's just that simple. So this 1 is attached to a double bond O and a hydrogen, so that's not chiral. Similarly, this carbon is attached to, this is basically a CH2, and it's attached to a OH. So that's not something we have to worry about. The area of interest is our 2, 3, and 4. So let's go ahead and actually write 2, 3, and 4. So it's second. Now, for time being, because we assume this hydrogen is in the front, just keep it be consistent. Assume it to be hydrogen to be in the front. That means the OH has to be in the back. Again, we assume hydrogen to always assume hydrogen to be in the front. We can always make the adjustment later. Okay, that's why I told you to assume hydrogen in the front, because that's why it makes life so much simpler. You know, we're not wasting time on this. Okay, now let's see if we have to make any changes at all, or it can be left as it is. So let's redo this. So this is 1, this is 2, this is 3 and 4. 1, 2, 3 counterclockwise front. Counterclockwise front is R, right? But that's not what we want, do we? We want S. So that means the OH has to go here, the hydrogen has to go here. Let's fix that, okay? Let's put a question mark on it. That means we have to change that, okay? And then, because I don't want you to keep changing as you do, because then it can get a little tricky. If you want to do that, that's fine. 1, again, this side will win the race because it's all the same, but this side has a double bond O. So 1, 2, 3, 4. 1, 2, 3. This is clockwise, right? Sorry about all the 1, 2, 3, 4s. It gets confusing. So clockwise front, and clockwise front is S. So again, that's not what we want. We want R. So let's put a question mark on it. Okay. Let's put a question mark, and finally on to the last one. 1, 2, 3, 4. So 1, 2, 3 again. That's counterclockwise, and counterclockwise front, right? Counterclockwise front is R. So that's correct. We do not have to make a change. This is checking out. So all we have to do now is come back and draw 5 carbons. And the end is the same, right? Again, I'm trying to make your life easy by doing all these adjustments so that when you do it, it's perfect. So all you got to do is bring the OH, because as it is drawn, it's giving R, but we want S, right? So swap positions. Means hydrogen should be in the back. Similarly, here, hydrogen was in the front, but we wanted R, so move the hydrogen to the back position. We had no problems here, so we're going to leave this as is. And that's it. This is the correct structure. We just went from Fischer to line, and that's exactly how we do it. I'll see you with one more example, and then I'm going to wrap this up and leave you with some practice problems. All right, so stay tuned.